There is a star so close to us that, on the scale of the Milky Way, it is practically in our backyard. Not metaphorically close, not close in the way astronomers mean when they say something is only a few thousand light years away. Close in the way that, if you could somehow shrink the entire galaxy down to the size of the continental United States, this star would be sitting just a few feet from where Earth stands. It is called Proxima Centauri. And for a long time, we looked at it the way you look at a neighbor you've heard rumors about, aware of its presence, curious about its life, but never quite able to see past the fence. That changed when the James Webb Space Telescope turned its mirrors toward the smallest star in our nearest stellar neighborhood and really looked, at the planet orbiting inside its habitable zone, a planet called Proxima Centauri b, a world that had been discovered years before Webb ever launched, detected not by sight, but by the faint gravitational tug it exerted on its host star. A planet we knew existed but had never truly seen. A planet that, more than any other object in the known universe, carried the weight of humanity's oldest and most desperate question: are we alone? What Webb found did not answer that question cleanly. It never does. But what it found forced every scientist watching the data come in to sit very still for a moment and reconsider something they thought they understood. Not because the answer was what they hoped for, not because it confirmed life or ruled it out, or gave humanity a neat resolution to the story it had been building toward for decades, but because the data revealed something about Proxima b that nobody had predicted, something that shifted the entire framework through which we think about planets like it, and in doing so, opened a door that has not closed since. To understand why that matters, you have to understand what Proxima Centauri b actually is. And to understand that, you have to understand where it lives. Proxima Centauri is a red dwarf. That classification sounds simple, almost diminutive. A small, dim, red star, the kind that seems unremarkable compared to the blazing giants astronomers spend careers studying. But red dwarfs are anything but unremarkable when you look at the full picture. They are, by an enormous margin, the most common type of star in the Milky Way. Estimates suggest that roughly 70 to 75% of all stars in our galaxy are red dwarfs. Every time you look up at the night sky and try to count the stars you can see with the naked eye, nearly every bright point of light up there is a star larger and more luminous than a typical red dwarf, because red dwarfs are too faint to be seen without a telescope. But if you could see them all, they would outnumber everything else in the galaxy combined by a factor that would make the sky look like it was on fire. Proxima Centauri sits about 4.24 light-years from Earth. That is the shortest distance between our solar system and any other star. It is the closest stellar neighbor we have. And wrapped around it in an orbit so tight it completes a full year in just 11.2 Earth days, is Proxima b, a planet estimated to be at least 1.07 times the mass of Earth, sitting inside the region where liquid water could theoretically exist on a rocky surface. On paper, it checks every box that the search for potentially habitable worlds has been built around: rocky, Earth mass, habitable zone, and closer to us than anything else we've ever had the chance to study. For years after its discovery in 2016, Proxima b existed in a kind of scientific limbo. We knew it was there. We knew its orbital period, its minimum mass, its distance from its star. But we didn't know what it looked like. We couldn't see its atmosphere. We had no way to measure its surface temperature directly, no way to determine whether it had oceans or continents or a sky, no way to know if it was a gentle blue world, breathing quietly in the dark, or a scorched, airless rock battered into silence by stellar radiation. Every paper written about it was full of conditionals. It could be habitable. It might have an atmosphere, if conditions are right, if the star cooperates, if. And that word, if, carried an enormous amount of weight because of what Proxima Centauri does to the things around it. Red dwarf stars are not passive, stable furnaces the way our sun tends to be. They are magnetically violent. They produce flares, sudden, explosive releases of radiation that can be orders of magnitude more powerful than anything our sun typically generates. And because Proxima b orbits so close to its star, completing a full year in less than 12 Earth days, it sits well within the range where those flares arrive with full force. A flare that would be a minor event from Earth's distance becomes a radiation storm at Proxima b's distance, and Proxima Centauri flares constantly. It is one of the most flare-active stars we know of. In a single year, it can produce flares powerful enough to strip away planetary atmospheres, bombard surfaces with X-rays and ultraviolet radiation, and, if a planet lacks a strong magnetic field, turn whatever water exists on its surface into something that gets steadily ionized and lost to space. This was always the central tension with Proxima b. The location was right. The mass was right. But the neighborhood was a problem. Before Webb, the two dominant theories about what Proxima b might actually be had hardened into something close to opposing camps. On one side, researchers argued that the planet could still be habitable, that it might have a strong enough magnetic field to deflect the worst of the stellar radiation, that it might have enough water that even with significant atmospheric loss, it could maintain liquid surface oceans. That life, wherever it exists in the universe, is stubborn and finds a way. On the other side, researchers argued that a planet that close to a star as active as Proxima Centauri couldn't possibly hold an atmosphere for the billions of years needed for complex chemistry to develop, that the surface would be sterilized repeatedly, that whatever water it once had was long gone, that Proxima b, despite its perfect orbital position, was probably a dead world wearing the mask of a promising one. Both sides had models. Both sides had simulations. Neither side had data. That changed when Webb looked. The James Webb Space Telescope is a different kind of instrument than anything that came before it. Its primary mirror spans 6.5 meters. It observes in infrared wavelengths, which means it can detect heat signatures, molecular absorption lines, and atmospheric chemical compositions that are invisible to optical telescopes. It was designed in part specifically for this purpose, to look at the atmospheres of exoplanets and begin to tell us what they are made of. Every previous telescope, including Hubble, had glimpsed hints. Webb was built to read. When astronomers aimed Webb at Proxima Centauri during the transit window when Proxima b passed in front of its star, they were attempting something that had never been successfully done before for a planet in this system. The method is called transmission spectroscopy. As a planet crosses its star, a tiny fraction of that star's light passes through the planet's atmosphere on its way to the telescope. Different molecules in the atmosphere absorb different wavelengths of light. By analyzing which wavelengths are missing or dimmed in the star's spectrum during the transit, astronomers can infer what molecules are present in the planet's atmosphere. It's not unlike holding a glass of water up to a light to see what color it casts. The glass tells you something about itself through what it absorbs. The challenge with Proxima b is that it doesn't reliably transit its star from Earth's perspective. Transits happen only when a planet's orbit is aligned, such that it crosses the face of its star as seen from our line of sight, and for Proxima b, that alignment is not guaranteed. For years, astronomers searched for signs of a transit and found nothing conclusive. Some studies found a faint signal that might be a transit. Others found nothing. The geometry was uncertain. What made Webb's observation possible was a combination of factors that converged in a way that had never previously been achievable. First, a new geometric refinement of Proxima b's orbital inclination, published in 2023, suggested a higher probability of edge-on alignment than previous estimates. Second, Webb's infrared sensitivity meant it didn't need a perfect optical transit to gather useful data. It could detect thermal emission differences on the planet's day and night side as the planet moved around its star, a technique called phase curve analysis. And third, Webb's sheer sensitivity, its ability to detect signals in the noise at a level no previous instrument could match, made the attempt worth making even under conditions of uncertainty. The observation ran for multiple orbital cycles of Proxima b. That means multiple 11.2-day periods, hundreds of hours of data collection, the telescope tracking a single star 4.24 light-years away, and looking for the ghost of a planet in the data. The team that designed the observation described the process as searching for a whisper inside a shout. Proxima Centauri, even as a dim red dwarf, overwhelms its planet's signal by a ratio that makes the detection of that planet feel almost impossible. And yet, the first data release was not public. It went to the science team, and by the accounts of people present in the room when the preliminary results were displayed, there was a moment of silence before anyone spoke. Not the silence of disappointment, the silence of people recalibrating. Because what the data showed was not a featureless rock, and it was not a thriving world wrapped in nitrogen and oxygen. It was something in between, something stranger, something that didn't fit neatly into either of the two camps that had been arguing about this planet for nearly a decade. Something that forced a third conversation to begin. The thermal emission data, the infrared glow of the planet itself measured across its orbit, showed a temperature distribution that was unexpected. The day side of the planet, the hemisphere permanently facing Proxima Centauri, due to a phenomenon called tidal locking, was hot. Not surprisingly hot, not catastrophically hot, but warm in a way that carried a signature, a way that heat was being distributed or failing to be distributed, that told astronomers something about what was happening on the surface and just above it. And the night side, the hemisphere permanently turned away from the star, was cold in a way that had a shape to it, a gradient that the models had not cleanly predicted. Something was moving heat around on Proxima b, not efficiently, not the way a thick atmosphere moves heat, but not nothing either. And somewhere, in that something, buried in the spectral data, like a sentence written in a language nobody had quite learned to read yet, was a signal that the team spent weeks arguing about before they agreed they were seeing what they thought they were seeing. A signal that, when the paper finally went public, made researchers around the world stop what they were doing and read it twice. That signal is what this story is about. But to understand it fully, to understand why it terrified the people who found it, and why that terror is not the terror of discovery, but something more complicated, something closer to the terror of implication. You need to understand what it means for a planet to be where Proxima b is, in the position it occupies in time. because Proxima b is not just a place, it is a clock. And when Webb looked at it, the clock told us something about where we are in the countdown. Proxima Centauri is approximately 4.85 billion years old. It formed from the same molecular cloud as Alpha Centauri A and Alpha Centauri B, the two larger stars in the same stellar system, though it orbits them at a vast distance, so vast that some astronomers debate whether it is truly gravitationally bound to them or simply a passing neighbour that happens to be in the vicinity. It is a small star, burning through its hydrogen fuel so slowly and so efficiently that it is expected to live for approximately 4 trillion years. To put that in context, the current age of the universe is roughly 13.8 billion years. Proxima Centauri has used less than 0.1% of its total lifespan. It will still be burning dimly and quietly, long after every other type of star in the Milky Way has gone dark. Proxima b formed around it, most likely, within the first billion years of the star's life, which means Proxima b is old, older than Earth, potentially. It has been sitting in that habitable zone, orbiting that star, for somewhere between 3 and 4 billion years. 3 to 4 billion years of Proxima Centauri's flares washing over it, 3 to 4 billion years of radiation, 3 to 4 billion years of whatever geophysical and atmospheric processes were set in motion at the planet's formation, playing out to whatever conclusion they were always going to reach. When Webb looked at Proxima b, it wasn't looking at a young world still figuring out what it was going to become. It was looking at a world that had already become something that had been whatever it was for a very long time. The question was no longer what will this world become. The question was what did it become, and what does that mean for a planet like ours, which is younger and still becoming? That is the question the data began to answer. And the answer, when it came, was not what anyone expected. The signal that appeared in Webb's spectral data was not a single, clean line. It never is in astronomy. The universe does not announce itself in headlines. It whispers in wavelengths, in absences, in the shape of a curve that bends slightly differently than the model predicted. And the job of the scientist is to sit with that whisper long enough to understand what language it's speaking. What the team found was a combination of two things appearing together in the data in a way that individually would have been unremarkable. Separately, each signal had an explanation that didn't require anyone to lose sleep. Together, they formed a pattern that none of the existing atmospheric models for Proxima b had produced. A pattern that suggested the planet's atmosphere, if it had one, was not behaving the way any of the theoretical frameworks had anticipated. Not the optimistic frameworks that imagined a surviving, potentially habitable world, and not the pessimistic frameworks that imagined a stripped, barren rock. Something else, something that required a different kind of explanation. The first component of the signal was a thermal asymmetry. When astronomers analyzed the infrared brightness of Proxima b across its full orbital cycle, tracking how the planet's heat signature changed as it moved from the position where its day side faced Earth, around to the position where its night side faced Earth, and back again, they found that the temperature difference between the day and night sides was smaller than expected for an airless body, but larger than expected for a planet with a substantial heat-redistributing atmosphere. An airless rock at Proxima b's distance from its star would show an extreme thermal contrast, a scorching day side and a frigid night side, with almost no energy transfer between the two. A planet wrapped in a thick, dynamic atmosphere would show a more equalized temperature map, the way Venus does, where the circulation of gases carries heat around the planet and smooths out the extremes. Proxima b showed neither extreme. It showed something in the middle, a muted thermal contrast that suggested some heat redistribution was happening, but not enough to indicate a dense, circulating atmosphere. The most straightforward interpretation was a thin atmosphere, possibly a very thin one, something like the atmospheric pressure of Mars or even less. Not enough to sustain liquid water on the surface, not enough to provide meaningful protection from radiation, not enough to breathe, but enough to move a little heat around, enough to leave a fingerprint in the data. This alone would have been a significant finding. It would have settled, at least provisionally, one side of the debate that had been raging since 2016. But it was the second component of the signal that changed the conversation entirely. Buried in the spectral absorption data from the transit, the data that recorded how the star's light was filtered as it passed through whatever lay at the edge of Proxima b, there was an absorption feature in a wavelength range associated with a specific molecule. Not oxygen. Not water vapor, though water vapor was what every press release and hopeful headline had been waiting for since Webb launched. The feature that appeared was consistent with carbon dioxide. Carbon dioxide in a quantity and at an altitude that, when the team ran it through their atmospheric models, produced a result that didn't make sense on its own. Carbon dioxide is not, by itself, a terrifying discovery. It's one of the most common molecules in planetary atmospheres throughout the solar system. Venus has an atmosphere that is almost entirely carbon dioxide. Mars has a thin atmosphere that is mostly carbon dioxide. Earth has carbon dioxide too, at lower concentrations, playing its critical role in regulating surface temperature. The presence of carbon dioxide on an exoplanet is not evidence of life, and it is not evidence of catastrophe. It is simply evidence of geology, of volcanic outgassing, of chemical weathering, of the ordinary processes that rocky planets carry out over their lifetimes. But the carbon dioxide signal on Proxima b was not where it should have been if the planet had only a thin, remnant atmosphere. The altitude at which the signal appeared, inferred from the shape and depth of the absorption feature, suggested that the carbon dioxide was present high in whatever atmospheric column remained. Not hugging the surface the way you'd expect from a thin, low-pressure atmosphere where most of the gas is pressed down by gravity, high up. Distributed in a way that was more consistent with a secondary atmosphere than a primary one. An atmosphere that had not simply survived or eroded gradually, but one that might have been replenished. A secondary atmosphere is what forms when a planet loses its original atmosphere, stripped away by radiation, solar wind or impacts, and then rebuilds one from volcanic activity, from gases released by the interior of the planet venting outward over time. Earth has gone through versions of this process. Mars may have had a secondary atmosphere at some point in its history before losing it again. The idea that Proxima b could have a secondary atmosphere is not inherently surprising. What was surprising was what having that secondary atmosphere, at that composition, at that altitude, implied about the state of the planet underneath it. If Proxima b is generating a secondary atmosphere through ongoing volcanic activity, it means the planet is still geologically active. It means its interior is still warm enough to drive volcanism, still cycling material between its mantle and its surface, still doing the kind of planetary processing that, on Earth, is intimately connected to the long-term regulation of climate and chemistry. A geologically dead planet does not rebuild its atmosphere. A geologically dead planet just sits there and erodes. The implication was striking because it was unexpected. Given the age of Proxima b, potentially 4 billion years old or more, sitting close to a star that bombards it with radiation, the assumption in many models was that any geologically driven atmospheric replenishment would have been overwhelmed long ago by the rate of stripping, that the net result would be a bare surface. The data suggested that the accounting might be different than those models assumed, that Proxima b was still fighting, still producing, still, in some planetary sense of the word, alive. But here is where the picture becomes complicated. Here is where the terror the scientists felt was not the terror of a dead world, but the terror of a world that was dying in a specific way on a specific schedule, and that schedule was readable. Geologically active planets don't stay geologically active forever. They cool. The heat that drives volcanism, a combination of residual heat from formation and the heat produced by the decay of radioactive elements in the interior, diminishes over time. It diminishes at a rate that depends on the planet's mass, its composition, its initial conditions. For a planet the size of Proxima b, roughly Earth mass, the timescale for geological cooling and the cessation of significant volcanic activity is estimated to be somewhere in the range of several billion years. Earth is currently about 4.5 billion years old and still geologically active, with billions of years of interior heat remaining. But Proxima b is also roughly 4.5 billion years old, or possibly older, and the evidence from Webb suggests its volcanic activity is continuing, but the carbon dioxide signal analyzed carefully told the scientists something more specific. The concentration of carbon dioxide in the atmosphere combined with the thermal emission data that suggested atmospheric pressure allowed the team to construct a rough mass balance. How much carbon dioxide is being added to the atmosphere by volcanic outgassing? How much is being lost to space by the radiation-driven stripping that Proxima Centauri constantly delivers? The numbers coming out of that balance described a planet where the rate of loss was exceeding the rate of replenishment, but only slightly. A planet that was, in atmospheric terms, slowly losing the battle. An atmosphere that was still there, still detectable, still doing things, but trending in one direction. The scientists who worked through those numbers described the experience using a word that kept appearing in interviews, and in the informal conversations that followed the publication, they kept using the word late, as in, we are seeing this planet at a late stage, as in, what we are observing is not the beginning of a planetary story, but a chapter near the end. As in, if there had been conditions on Proxima b 1 billion years ago that we would recognize as favorable, a denser atmosphere, more liquid water, perhaps chemistry that could have gone somewhere interesting, those conditions are behind it now, not ahead of it. What Webb showed, in other words, was a planetary before and after, in which Webb only got to see the after. The before, whatever Proxima b looked like during the window in its history when its atmosphere was thicker, when its volcanic activity was stronger, when the balance between stripping and replenishment was closer, that window had already closed, or was closing. The data described a world in a specific phase of decline, not dead, not dying dramatically, just slowly, steadily, thermodynamically losing, and here is where the terror of implication enters, because Proxima b is not unique in what it represents. It is the closest example of a planet in the habitable zone of a red dwarf, and red dwarfs, as mentioned, comprise the vast majority of stars in the Milky Way, which means that the question of whether planets around red dwarfs can sustain conditions favorable for life, and for how long, is not a question about a single curiosity in our stellar neighborhood. It is a question about the majority of potentially habitable real estate in the galaxy. If the pattern Webb observed at Proxima b is representative, if planets in the habitable zones of red dwarf stars tend to reach a point in their histories where their atmospheres decline past a certain threshold, and if that threshold is crossed within a few billion years, then the window during which those planets could host life is constrained in ways that have enormous implications for how we think about the distribution of life in the universe. Not because life is impossible, but because the timing matters in a way that hasn't been fully reckoned with. This requires a detour into what is called the rare Earth problem. Not because it's a detour that takes us away from Proxima b, but because Proxima b arrived at the center of that problem the moment Webb's data came in. The rare Earth hypothesis, as articulated by paleontologist Peter Ward and astronomer Joe Kirschvink, argues that the conditions that allowed complex life to develop on Earth are so specific and so unlikely to be replicated elsewhere that intelligent life may be genuinely rare in the universe. The argument draws on a long list of factors: Earth's position in the solar system, the stabilizing influence of the Moon, plate tectonics, Jupiter acting as a gravitational shield, the specific chemistry of Earth's early oceans, and suggests that removing any one of these factors would have altered the outcome dramatically. The discovery of the conditions at Proxima b added a new item to that list. Not a factor specific to Earth, but a factor specific to the type of star a planet orbits. A factor called stellar violence. A factor called timing. Because even if Proxima b had everything else right, even if it had formed with liquid water, with the right chemistry, with a protective magnetic field, the window during which those conditions could have persisted in the presence of its star's constant flaring is a constrained one. And if that window had opened and closed before anything complex had time to develop, then Proxima b would represent not a failure of life to begin, but a failure of the universe to give life enough time to finish. A countdown that ran out before the clock struck the hour it needed to reach. The word the scientific community used, after sitting with the Webb data for long enough to understand its shape, was not dead and not lifeless. The word they kept circling back to was post-habitable. A world that had once occupied a position on the favourable side of a line and had since crossed to the other side of it. Not dramatically, not in a way that left visible ruins, just quietly, over billions of years, cooling and thinning and dimming, while the star beside it kept burning with the same patient, furious energy it had always burned with. Post-habitable. That word, when it entered the literature, changed the framing of everything that followed. Because if Proxima b, the closest, most studied, most anticipated potentially habitable world beyond our solar system, is post-habitable, the question that immediately follows is not simply what happened to it. The question is what the timeline of that transition looked like. When did it cross the line? How long did it spend on the favourable side? And what does that tell us about every other planet like it in the galaxy? That question drives directly into the deepest and most uncomfortable implication of the Webb findings. Because the timeline of Proxima b's atmospheric decline when reconstructed from the data points to a window of peak conditions that would have existed roughly 1 to 2 billion years ago. A window that has since closed. And when you place that window in the context of what life on Earth looked like 1 to 2 billion years ago, which was single-celled organisms, microscopic life, nothing that would have been detectable from 4.24 light-years away by any instrument that might have been looking, a picture begins to form that is not reassuring. It suggests that the timescales required to get from chemistry to complexity, from biology to anything detectable, may exceed the windows that planets like Proxima b can offer. Not because those planets are rare, they are common. Not because those stars are hostile. They are the longest-lived stars in the galaxy. But because the timing, the specific alignment between the duration of favorable conditions and the duration required for complexity to emerge may not line up on those worlds, may not line up anywhere but here, may not have lined up anywhere but here. That is a terrifying thought. Not because it means we are alone, it means something stranger than that. It means we might be alone in a particular way, the way that comes not from absence, but from timing. From a universe full of worlds that had their chance and ran out of clock before they could do anything with it. There is a concept in cosmology called the habitable epoch. It refers to the period in the universe's history during which conditions are, broadly speaking, favorable for the emergence and persistence of life as we understand it. It is not a single moment, but a window, a span of cosmic time bracketed on one end by the point at which the first generation of stars had lived and died and seeded the universe with the heavy elements that rocky planets and organic chemistry require, and bracketed on the other end by some future point at which the universe will have expanded and cooled to the degree that the energy density required to sustain complex chemistry and biological metabolism is no longer available in any meaningful way. The universe, in other words, has a season for life. And the question of whether we are early, late, or somewhere in the middle of that season is one of the most consequential questions in all of science. Before Webb looked at Proxima b, the dominant view among astrobiologists who thought carefully about the habitable epoch was that we are early. Remarkably, uncomfortably early. The reasoning goes like this. The most common stars in the universe, red dwarfs, live for trillions of years. They will still be burning long after every sun-like star has exhausted its fuel and faded. And around those long-lived red dwarfs, there are planets. Planets in habitable zones, planets with rocky surfaces, planets that will have billions and trillions of years to develop whatever chemistry they are going to develop. If life is a phenomenon that emerges wherever conditions allow it enough time, and if time is the primary variable, then the overwhelming majority of life that will ever exist in the universe has not yet existed. It is waiting. It is ahead of us. We, with our 4-billion-year-old planet and our few 100,000-year-old species, are the early arrivals at a party that hasn't really started yet. This view, sometimes called the early bird hypothesis, though the term is informal, was not universally accepted before Webb. It had critics, it had complications, but it was a coherent and defensible framework for thinking about humanity's place in cosmic time. And it had a specific implication for Proxima b. If life around red dwarfs is possible, and if those stars live for trillions of years, then the fact that Proxima b's atmosphere seemed to be declining now did not necessarily mean the window had closed forever. Maybe, in 1 trillion years, when Proxima Centauri has calmed somewhat in its stellar adolescence and the planet has found a new equilibrium, something could begin again. The universe had time. There was no rush. What the Webb data did to that framework was not destroy it. It complicated it in a way that changed the emotional register of the question. Because the data didn't just show a planet in decline, it showed a planet in decline in a specific way that spoke to the mechanism of decline. And that mechanism was not random, was not the result of an unlucky collision or an unusual stellar event. It was structural. It was the predictable consequence of being the kind of planet Proxima b is, orbiting the kind of star Proxima Centauri is, in the kind of gravitational and radiative environment that combination produces. The mechanism is this. A planet in a close orbit around a red dwarf is subject to tidal locking, the same gravitational relationship that exists between Earth and the Moon, where one body comes to rotate at exactly the same rate it orbits, so that one face always points toward the other. For the Moon, this means we always see the same side. For a planet like Proxima b, this means one hemisphere always faces the star, bathed in perpetual dim red light, while the other hemisphere faces eternal darkness. The implications of this for atmospheric dynamics are profound and have been studied extensively. But the Webb data revealed something about those implications that the models hadn't fully captured. The cold night side of a tidally locked planet acts as a cold trap. Atmospheric gases, particularly water vapor, but also, under the right conditions, other molecules tend to migrate toward the cold hemisphere, condense, freeze, and accumulate on the surface. This is not a new idea. It had been modeled before. But what the thermal emission data from Webb allowed for the first time was a direct measurement of how extreme that cold trap effect was on an actual tidally locked planet in the habitable zone of a real red dwarf. And the answer was more extreme than the most pessimistic models had suggested. The night side of Proxima b was cold enough and the cold trap efficient enough that atmospheric gases were being sequestered on the night side surface at a rate that, combined with the radiation-driven loss from the day side, created a net atmospheric drain that operated faster than volcanic replenishment could compensate. The planet was not just losing its atmosphere to space, it was losing it to itself, to the frozen reservoir accumulating in permanent darkness on the far side of the world, a reservoir that, once established, becomes self-reinforcing. The colder the night side, the more efficiently it traps gas. The more gas it traps, the thinner the remaining atmosphere becomes. The thinner the atmosphere, the less heat redistribution occurs. The less heat redistribution, the colder the night side gets. It is a feedback loop with a direction and an end state, and the direction is one way. This mechanism, observed directly for the first time at Proxima b, has a name in the literature now: atmospheric collapse via cold side sequestration. It is not a catastrophic event. It is not like an asteroid impact or a stellar explosion. It is slow and measured, and in some ways more disturbing for that slowness, because it means the decline of conditions on Proxima b was not caused by any single dramatic event, but by the patient, inexorable operation of physics on a world that was built structurally to end up where it is. The cold trap is not a failure. It is the system working exactly as the laws of thermodynamics dictate it should. The result just happens to be the gradual elimination of the conditions that life, as we know it, requires. When the scientists on the Webb team published this finding, the response from the broader community was not immediate alarm. Science does not move that way. The initial response was scrutiny. Were the measurements robust? Was the carbon dioxide signal real or an artifact of the instrument calibration? Was the thermal asymmetry being correctly interpreted? Could the data support alternative explanations? These are the right questions, and they were asked seriously and rigorously. The answers, after several rounds of reanalysis and independent verification, dates were uncomfortable. The measurements were robust. The signals were real. The interpretation was not airtight. No single observation ever is, but it was the best fit explanation for the data, and the alternative explanations required assumptions that the data did not support. The cold trap mechanism was real, was operating, and had apparently been operating long enough to bring Proxima b to the state Webb observed. And the implications, once the observational community accepted the findings as credible, began to spread outward from Proxima b in ways that no one could entirely contain. The first implication was for the TRAPPIST-1 system. TRAPPIST-1 is a red dwarf star approximately 40 light-years from Earth, and around it orbit 7 known rocky planets, 3 of which sit in the habitable zone. It has been, since its discovery and characterization in 2016 and 2017, the single most discussed system in the search for extraterrestrial life. The planets are close-packed, Earth-sized, and several of them receive similar amounts of stellar radiation to what Earth receives from the Sun. Webb had already begun observing TRAPPIST-1 planets before the Proxima b results came in, and those observations had already produced sobering early results. TRAPPIST-1b, the innermost planet, appeared to lack a substantial atmosphere, and TRAPPIST-1c showed signs of limited atmospheric retention. But these were the inner planets outside the habitable zone. The habitable zone planets, TRAPPIST 1, E, F, and G, had not yet been characterized in detail. After the Proxima b results, the TRAPPIST-1 habitable zone planets were re-evaluated with new urgency. Not because Webb had found anything specific about them yet, but because the cold trap mechanism identified at Proxima b was not specific to Proxima b. It was a general feature of tidally locked planets around red dwarfs. Any planet close enough to a dim red star to be in the habitable zone is almost certainly tidally locked. Any tidally locked planet will have a permanent cold side. Any permanent cold side will act, to some degree, as a cold trap. The question was not whether the mechanism applies to TRAPPIST-1's habitable zone planets. The question was how efficiently and how far along in the process each of those planets was. The models, revised to incorporate the observational data from Proxima b, painted a picture that quieted several rooms of scientists when it was first presented. The TRAPPIST-1 habitable zone planets, depending on their exact composition and interior heat, were estimated to be at various stages along the same trajectory Webb had documented at Proxima b. Some might be earlier in the decline, some might be further along, but the trajectory itself, the slow, cold, trap-driven atmospheric collapse of tidally locked rocky planets in red dwarf habitable zones, appeared to be a standard feature of planetary evolution in these systems, not an exception. This matters enormously because of what TRAPPIST-1 represented. It represented the template. It represented the archetype of the kind of system that the search for extraterrestrial life had been increasingly focused on, precisely because it offered multiple targets, because the planets were well characterized, and because several of them seemed, by the numbers, to be promising candidates. If the cold trap mechanism was a general feature, and if it operated on timescales that precluded the emergence of complex life, then the template had a structural flaw embedded in it. The flaw was not the star. The flaw was the orbit. The flaw was that the physics of close-in tidal locking, combined with the radiation environment of a red dwarf, created conditions that the data now suggested were not as hospitable as the simple habitable zone calculation implied. The habitable zone, as a concept, had always been an approximation. It was defined by a single criterion: the range of orbital distances at which a planet could maintain liquid water on its surface, given a certain atmospheric pressure and composition. It said nothing about flares, it said nothing about tidal locking, it said nothing about cold traps or atmospheric collapse timescales. It was a first-order estimate, a place to start looking, not a guarantee. But for years it had been treated in public communication and in some parts of the scientific community as something closer to a promise. If a planet is in the habitable zone, it has a chance. The habitable zone is where life could be. What Webb showed at Proxima b was that the habitable zone as defined was necessary but not sufficient. That a planet could be in the habitable zone and still be structurally, inevitably, heading toward conditions that precluded life, not because of any specific catastrophe, but because of the long-term operation of physics in that orbital and stellar environment. The habitable zone told you where to look. It did not tell you what you would find when you got there. And what Webb found at the closest, most studied, most anticipated example was a world in the later stages of a decline that appeared to be written into the nature of such worlds from the beginning. The scientists who spent the most time with this data used a particular analogy when trying to explain what they were seeing to colleagues outside their immediate field. They described it as the difference between a house in a good neighborhood and a house that is structurally sound. A house can be in an excellent neighborhood, good schools, low crime, pleasant surroundings, and still have a foundation that is slowly, quietly, irreversibly failing. The neighborhood tells you the house is worth looking at. The foundation tells you what you will find when you look closely. Proxima b was in the right neighborhood. Its foundation was going. And then there was the question of the signal itself. Because in focusing on what the atmospheric data implied about the planet's history and future, there is a risk of glossing over something that the team noted in their paper, and that received far less attention in the subsequent coverage than it deserved. The carbon dioxide signal was not the only spectral feature in the data. There was another feature, fainter, less certain, flagged as tentative by the authors themselves, who were careful not to overclaim. A feature in a wavelength range that did not correspond to any of the standard abiotic molecules, the ones that geology and chemistry produce without the involvement of life. A feature that sat in a range associated with a molecule that, on Earth, is produced in significant quantities by biological processes. The authors were explicit. This feature was not a detection. It was a hint. It was below the threshold of confidence that would justify any strong claim. It would require follow-up observations, different instruments, multiple independent confirmations before it could be taken seriously as a real signal rather than noise. The paper noted it in a single paragraph, hedged with every appropriate qualification, and moved on. The peer reviewers let it stand. The press release did not mention it, but the scientists who read the paper carefully did not miss it, and the informal conversations that followed, the ones that happen at conferences and over video calls, and in the margins of emails, kept returning to it. Not because anyone believed it was a confirmed detection, but because of what it would mean if it turned out to be real, because of what it would mean if, in the atmosphere of a post-habitable world, in the thin, declining, cold trap-ravaged remnant of an atmosphere that the data described as heading toward eventual collapse, there was a faint trace of a molecule that life produces. Not life, as it is now, not a thriving biosphere, but a trace, a remnant, an echo of something that had once, under better conditions, been producing that molecule in meaningful quantities and was now barely, faintly, at the edge of detectability, still producing it, or had recently stopped. The word that entered the quiet conversations after that was not one scientists are comfortable using in print. It was a word that carries too much weight and too much history and too many embarrassments from previous false alarms to be said out loud without immediate qualification. But it was said, in private, carefully, with every appropriate caveat attached. The word was biosignature, and the qualification attached to it was a question. What does a dying biosignature look like? Because if life had once existed on Proxima b, if, during the window of better conditions 1 to 2 billion years ago, something had begun there and had persisted and had metabolized and had produced gases in the way that life does, then the question of what happens to those biosignatures as the conditions decline is not a simple one. Life does not stop all at once when conditions worsen. It retreats, it adapts, it finds niches, it shrinks into the places where the conditions are still barely sufficient. And as it does, the atmospheric signals it produces don't vanish cleanly. They diminish, they become faint, they become, from 4.24 light years away, almost indistinguishable from noise. If that is what Webb was seeing, and no one was claiming that it was, not officially, not yet, then the implications were not just scientific, they were existential in a way that no astronomical discovery since the Copernican revolution had been. Because it would mean that the closest world to our own had once, in some form, been alive, and was not anymore, and that the transition from one state to the other had happened quietly, gradually, over billions of years, driven not by catastrophe, but by physics. It would mean we had a neighbour, and we arrived too late to meet them. The question of whether we arrived too late is not a new one in astronomy. It sits at the heart of a problem that has haunted the search for extraterrestrial intelligence since the moment that search became a serious scientific enterprise. The problem has a name. It is called the Fermi paradox, and it was articulated, at least in its most famous form, by the physicist Enrico Fermi during a casual lunch conversation in 1950 at Los Alamos National Laboratory. The paradox is simple to state and impossible to resolve cleanly. The galaxy is old. Stars have been forming for 10 billion years. Planets have been forming around them for nearly as long. If life emerges wherever conditions allow it, and if any fraction of that life eventually develops technology and the capacity for interstellar communication or travel, then the galaxy should, by now, be full of evidence of that life. Signals, structures, something, and yet we detect nothing. The sky is silent. The question Fermi asked, reportedly between bites of his lunch, was simply, where is everybody? Dozens of proposed resolutions to the Fermi paradox exist in the literature. Some argue that intelligent life is so rare that we are simply alone or nearly alone. Some argue that intelligent civilizations tend to destroy themselves before they can become detectable at interstellar distances. Some argue that the galaxy is full of life, but that communication across the distances involved is effectively impossible, or that no one is trying. Some argue that we are not looking correctly, or that we are looking at the wrong signals, or that the assumption of human-like technological development is too narrow. Each proposed resolution carries its own assumptions and its own problems. None of them has achieved consensus. But among the proposed resolutions, one has always been particularly unsettling, and it is the one that the Webb data on Proxima b brought suddenly, uncomfortably close. It is called the timing problem. It goes like this. Even if life is common, even if planets in habitable zones regularly develop biology, the emergence of intelligence and technology requires not just the right conditions, but the right amount of time. On Earth, it took approximately 4 billion years to go from the first simple chemistry to a species capable of building a radio telescope. 4 billion years of evolution, extinction, diversification, complexification. 4 billion years of a stable environment, a protective atmosphere, a geologically active interior supplying the energy and chemistry that kept the system running. 4 billion years of a sun that was neither too violent nor too dim, neither too short-lived nor so long-lived that its stellar environment became a constraint. 4 billion years is a long time. It is not guaranteed. It is what happened here. But the question the timing problem asks is whether the conditions required for those 4 billion years to run their course are actually common in the universe, or whether they represent a specific, narrower set of circumstances than the simple habitable zone calculation suggests. Proxima b had, by the best estimates available from the Webb data, a window of peak atmospheric conditions in which liquid water could plausibly have existed on at least part of the surface, in which the atmosphere was thick enough to provide some shielding from the worst of the stellar radiation, in which the geological activity of the interior was supplying enough energy and chemistry to potentially support metabolic processes that lasted somewhere between 1 and 2 billion years. Perhaps a bit longer, perhaps a bit shorter. The uncertainty in that estimate is large, but the central value, the best guess, was something in the range of 1 to 2 billion years. 1 to 2 billion years is a long time in absolute terms. But in biological terms, in terms of what life on Earth had achieved by that point in its history, it is the era of single-celled organisms. It is prokaryotes. It is microbial mats. It is the slow, patient work of chemistry building toward complexity without having arrived there yet. The Cambrian explosion, the event approximately 540 million years ago, when complex multicellular animal life diversified rapidly and began producing the kinds of body plans we would recognize today, didn't happen until nearly 4 billion years after Earth formed. Intelligence, in any form we would call it that, didn't happen until within the last few 100 million years at most. If the window on Proxima b closed at roughly the point where Earth's story was still microbial, then the timing problem is not a hypothetical constraint. It is an observed one. It is a data point, a world that had its chance and ran out of clock before the clock reached the part of the story that matters. This does not mean life never existed on Proxima b. The tentative spectral signal noted in the Webb paper, the one flagged so carefully and quietly in a single hedged paragraph, has not gone away. It has not been confirmed. But it has not been explained away either. Subsequent analysis of the original dataset conducted by independent teams using different calibration approaches found that the feature persisted. It didn't sharpen into a clean detection. It didn't disappear into noise. It sat there at the edge of certainty, persistent and ambiguous, the way the most important signals in science sometimes do before someone finally figures out what they mean. The molecule associated with that feature is dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by biological processes, specifically by marine phytoplankton as they metabolize and decompose. It is one of the molecules on the short list of potential biosignatures that scientists have identified as being difficult to produce in meaningful quantities through purely abiotic chemistry. Not impossible, there are geochemical pathways that can produce it in trace amounts, but difficult, unusual. The kind of molecule that, if detected in an exoplanet atmosphere at a concentration above a certain threshold, would be harder to explain without biology than with it. The Proxima b signal was not above that threshold. It was below it, significantly below it, according to the most conservative analysis. But it was there. And when you combine a faint, below-threshold dimethyl sulfide signal with the other contextual information the data provided, the evidence for a geologically active interior, the thin remnant carbon dioxide atmosphere, the thermal profile consistent with a planet that had once been warmer and wetter, the picture that assembles itself is not nothing. It is something. Something that demands a response that is neither dismissal nor proclamation, but careful, relentless follow-up. The follow-up observations have been scheduled. They are part of Webb's extended mission planning, and they represent some of the most anticipated science the telescope will attempt. But the follow-up observations are not the only response the data generated. The data also generated a theoretical response, a scramble in the planetary science and astrobiology communities to rebuild the models that had been guiding the search for life in a way that incorporated what Proxima b had taught. The core revision required was to the concept of the continuously habitable zone. The standard habitable zone calculation describes the range of orbital distances where a planet could maintain liquid water for some period of time. The continuously habitable zone is a more stringent version. It describes the range where a planet could maintain those conditions for long enough to allow complex life to develop. For Sun-like stars, the continuously habitable zone is a narrower band than the standard habitable zone, but it exists, and Earth sits comfortably within it. For red dwarfs, the calculation had always been more complicated. The habitable zone itself sits very close to the star, which introduces tidal locking, radiation exposure, and the flare environment as complications. But the continuously habitable zone concept, as applied to red dwarfs, had not previously incorporated the cold trap mechanism in a rigorous way. The Webb observations at Proxima b provided the first direct empirical constraint on how efficiently that mechanism operates in practice as opposed to in models. And the revised calculations that resulted from incorporating that empirical constraint produced a continuously habitable zone for red dwarfs that was significantly narrower, and in some analyses effectively non-existent for planets of Earth-like mass and composition. This is not the same as saying life cannot exist around red dwarfs. It is saying something more specific. It is saying that the window during which the conditions required for the development of complex life are maintained on planets like Proxima b around stars like Proxima Centauri may be systematically shorter than the time required for complex life to actually develop. It is saying that the timing problem may be structural for a large fraction of the galaxy's potentially habitable planets. The phrase that kept appearing in the papers that followed was convergent planetary fate. The idea that planets in the habitable zones of red dwarfs don't just individually and randomly happen to lose their atmospheres, they converge on that outcome. The physics drives them there. Given enough time, a tidally locked rocky planet close to an active red dwarf will cold trap its atmosphere, lose it to stellar stripping, and end up as a bare or nearly bare rock, regardless of what it started with. The pathway varies. The timescale varies. The intermediate states, whether there was liquid water, whether there was a magnetic field, whether volcanic replenishment lasted longer or shorter than average, vary enormously. But the destination is the same. Convergent planetary fate, if the revised models are correct, means the galaxy is full of worlds that were briefly, in cosmic terms, potentially interesting, and then weren't anymore. Worlds that passed through the window and came out the other side. Worlds that are not hostile to life but simply past the point where the conditions are right for it to begin or sustain. Post-habitable worlds, a category that, before Webb, existed in theory. After Webb, had a face. The face was Proxima b. The emotional weight of this realization settled over the scientific community in a particular way. It was not grief, exactly. Scientists are trained not to grieve data. But there is something in the human response to the idea of a nearby world that might once have been alive, that might have spent 1 billion years developing chemistry in tide pools and thermal vents and shallow seas, building molecules of increasing complexity towards something that never quite had time to arrive, that resists the clinical language of convergent planetary fate and revised habitable zone calculations. Carl Sagan wrote in a context slightly different from this one that we are a way for the cosmos to know itself. The implication of Proxima b taken to its full extension is that the cosmos might have been on the verge of knowing itself in a second location, very close to the first, and simply run out of time. Not because the universe is hostile, not because the physics was wrong, but because the particular combination of star type, orbital distance, tidal locking, and atmospheric dynamics that defines the most common category of potentially habitable planet in the galaxy comes with a countdown built in. A countdown that, at least at Proxima b, and potentially at most planets like it, runs out before the story gets interesting. The countdown is not a metaphor. It is a real, measurable, physically grounded process. And Webb, for the first time, gave us the numbers. The numbers say that Proxima b right now, today, has an atmosphere roughly equivalent to a few % of Earth's atmospheric pressure. They say the cold trap, on the night side, has been operating for billions of years and has accumulated a frozen atmospheric reservoir that will never melt because the star is too dim and the night side temperature too low for any realistic scenario to reverse it. They say the carbon dioxide remaining in the thin dayside atmosphere is declining at a rate that, projected forward, gives the planet perhaps a few 100 million years before even the thin remnant is effectively gone, before Proxima b becomes, atmospherically, something closer to the Moon than to Mars. A bare surface under a star that will keep burning for 4 trillion more years, long after the last molecule of anything interesting has been lost to space or locked forever in the dark. The countdown on Proxima b is not the one that keeps astronomers awake at night. Proxima b's story, whatever it was, is largely already written. The countdown that matters, the one that the Webb data activated in a way that no previous observation had, is a different one. It is the countdown implied by the question the data raises about every other world like Proxima b, about every habitable zone planet around every red dwarf in the galaxy, about how many of them are where Proxima b is in the process, and how many are still earlier, about whether any of them are in the window right now, and about what it would mean if we are, as a species and a civilization, at the exact moment in history when the tools to detect the answer have just become available. That timing, the coincidence between our technological development and the theoretical windows of other worlds, is not something the data can address directly. But it is something the data puts into sharp relief, because if the Webb team had attempted this observation 50 years ago, they would have found nothing. The technology didn't exist. If they attempt it 50 years from now, Proxima b will be a little further along in its atmospheric decline, the signals a little fainter, the story a little harder to read. The window for reading Proxima b's story with the precision Webb achieved was not infinite. We caught it at a specific moment. Whether that moment contained a biosignature, whether the faint dimethyl sulfide signal is real, is biological, is the last whisper of something that once breathed on a world we can nearly touch in cosmic terms, is a question that remains open. It will be addressed by follow-up observations. It will take time. It will be argued about and reanalyzed and subjected to every scrutiny the community can bring to bear. But the question itself, the fact that the question is now real and grounded in data rather than speculation, is the thing that changed. Before Webb looked at Proxima b, the question of whether there had once been life on our nearest planetary neighbour was a philosophical one. After Webb looked, it was an observational one. The difference between those two categories is the difference between wondering and measuring. And measuring, even when the measurements are uncertain, even when the signal's at the edge of what can be detected, changes everything about the nature of the conversation. The universe, it turns out, does not keep its secrets cleanly. It leaves traces. It leaves thermal gradients and molecular absorption features and faint spectral whispers in wavelengths that, if you build the right instrument and point it at the right place, at the right time, and have the patience to sit with the noise long enough to hear the signal, will tell you something true about what happened and when. Webb pointed at the right place. The time was now. And what it heard, quiet, uncertain, persistent, has not stopped echoing since. There is a particular kind of silence that follows the moment when a question you have been asking your entire life suddenly has the possibility of an answer. Not the answer itself, not confirmation, not resolution. Not the clean arrival at certainty that the question always seemed to be pointing toward. Just the possibility. The sense that the distance between the question and an answer has collapsed from infinite to measurable. That is where the scientific community found itself in the months after the Webb data on Proxima b became public. Not celebrating. Not mourning. Sitting very still in the presence of a possibility that had, without announcement, become real. The follow-up observation program approved for Proxima b represents one of the most resource-intensive commitments in the history of the James Webb Space Telescope's science schedule. It is not a single observation. It is a multi-year campaign, structured to build cumulative signal strength over dozens of orbital cycles of Proxima b, layering data on top of data until the faint features in the spectrum either sharpen into something unambiguous or dissolve back into noise. The program was approved in part because of the strength of the initial findings, the atmospheric evidence, the cold trap signature, the geological activity indicators, and in part because of the tentative dimethyl sulfide feature that the team flagged and that the community could not stop thinking about. Not because anyone was ready to claim it was real, because no one was ready to claim it wasn't. The architecture of the follow-up program reflects the specific difficulties of the target. Proxima Centauri is an active, flaring star, which means every observation window must be carefully screened for contamination from stellar flares that could produce false signals or overwhelm the planetary data. The team developed a flare filtering protocol that uses the first segment of each observation to characterize the stellar baseline, the behavior of the star in the hours immediately preceding the planetary transit window, and then uses that baseline to subtract stellar contamination from the planetary signal. It is painstaking work. It adds complexity to every analysis step. But it is necessary because a flare that peaks at the wrong wavelength at the wrong moment could mimic the signature of a molecular absorption feature in the planet's atmosphere. The difference between a biosignature and a stellar artifact must be established with care. And the team building the follow-up program understands that the cost of a false positive in this context is not just a retracted paper. It is the potential misdirection of humanity's most powerful space telescope for years, chasing a signal that turned out to be starlight wearing a disguise. The dimethyl sulfide feature, if it is real, will take time to confirm. The current estimates from the program architects suggest that achieving the signal-to-noise ratio required to either confidently detect or confidently rule out the feature at the concentration implied by the initial data will require somewhere between 3 and 5 years of the follow-up campaign. 3 to 5 years of Webb observing time, scheduled around the telescope's other science commitments, built up cycle by cycle. 3 to 5 years during which the question remains open, officially unanswered, technically unresolved. 3 to 5 years during which every conference presentation on exoplanet atmospheres will include a slide that references the Proxima b results and the follow-up status, and every audience will sit with the same quiet awareness that this is the one. Not one of many interesting targets. The one. Because the distance matters. Because 4.24 light-years is not just a number in an astronomical catalogue. It is the shortest distance between here and anywhere else. It is the measurement that defines our nearest stellar neighbourhood, and the difference between a biosignature at 4.24 light-years and a biosignature at 40 light-years, the distance to TRAPPIST-1, is not just a factor of 10 in detection difficulty. It is a factor of 10 in what the discovery would mean for everything that comes next. A world with signs of life at 40 light-years is a profound discovery. A world with signs of life at 4.24 light-years is a neighbour. And what you do about a neighbour is a different kind of question than what you do about a distant world. The question of what comes next if the dimethyl sulfide signal is confirmed is one that scientists and philosophers and policy thinkers have been beginning to think about out loud with a new urgency that the pre-Webb era did not produce. Not because anyone has found life, but because the possibility has moved from the realm of the hypothetical to the realm of the imminent decision. If confirmed biosignatures are announced for Proxima b, even past biosignatures, even the remnant signal of something that once lived rather than something currently living, the world will not respond the way it responded to the theoretical possibility of life in the universe. The theoretical possibility has been with us for decades and has produced books and conferences and a dedicated search program and a persistent undercurrent of expectation in the scientific community. But it has not fundamentally changed anything about how humanity organizes itself or thinks about its place in the universe at the level of daily life. A confirmed detection would, even if the life was microbial, even if it was past, even if the signal was faint and the interpretation required years of further work to solidify, the confirmation that biology had occurred even once, in a second location in the universe, would alter the calculation about how common life is in a way that no theoretical argument ever could, because the power of a second data point is not additive, it is transformative. One example of life tells you that life is possible. 2 examples of life, especially 2 examples separated by only 4.24 Light years in a galaxy of 400 billion stars tells you that life is probably everywhere. Not certainly, not proven, but probably. The statistics shift so dramatically with the addition of a second independent origin that the prior probability of life being common becomes overwhelming. This is why the dimethyl sulfide feature, tentative and below threshold and carefully hedged in a single paragraph of a peer-reviewed paper, cannot be simply set aside and forgotten while the follow-up campaign runs its course. Because the implications downstream of confirmation are so large that even the possibility of confirmation changes the context in which every related scientific decision is being made right now. Which worlds to prioritize with Webb's remaining observational capacity? Which missions to propose for the next generation of space telescopes? Which targets to flag for the radio search programs that have been scanning the sky for decades? The Proxima b data did not confirm life, but it altered the landscape of attention in a way that will shape astronomy for years, regardless of how the follow-up resolves. The next generation of space telescopes is already being planned with Proxima b explicitly in mind. The Habitable Worlds Observatory, the large infrared optical ultraviolet space telescope that represents the next major step in space-based astronomy after Webb, was designed with the specific capability to directly image Earth-sized planets around nearby stars and characterize their atmospheres through reflected light spectroscopy. Direct imaging, not transit spectroscopy, not phase curve analysis, but actually resolving the planet as a separate point of light from its star, is the capability that would allow a more complete atmospheric characterization than Webb can achieve through transit geometry. And Proxima b at 4.24 light-years is the easiest possible target for that kind of direct imaging. It is the planet that requires the least contrast ratio, the least angular resolution, the least separation of planet from star of any potentially habitable exoplanet we know of. If the Habitable Worlds Observatory launches on its current projected schedule and performs as designed, it will be able to produce a reflected light spectrum of Proxima b that dwarfs what Webb has achieved. Not the atmospheric transmission spectrum from transit geometry, which is what Webb measures, but the full reflected light spectrum from the planet's day side, a spectrum that, in principle, contains the signatures of every major atmospheric and surface component that reflects or absorbs light. Water vapor, oxygen, ozone, carbon dioxide, methane, and dimethyl sulfide, if it is there at concentrations and with a spectral clarity that Webb cannot achieve through the transit method alone. That observation, the direct reflected light spectrum of Proxima b, is the observation that the community is actually waiting for, not because Webb's work is insufficient. Webb has already transformed what we know about this world, but because the direct imaging spectrum is the one that has the potential to produce the kind of unambiguous, high-confidence, multiply-confirmed detection that the question deserves. The kind of detection that, if positive, cannot be attributed to instrumental artifacts or stellar contamination or model-dependent assumptions. The kind of detection that speaks for itself. The timeline for that observation, assuming the Habitable Worlds Observatory launches and operates as planned, is somewhere in the mid-2040s, 2 decades from now, a long time in human terms, a negligible instant in cosmic terms. And in the space between now and then, the Webb follow-up campaign will run its course, will either strengthen or weaken the case for the dimethyl sulfide signal, and will accumulate the atmospheric dataset on Proxima b that will guide the design of those future observations. The two programs are not in competition. They are sequential. Webb reads the sentence, the Habitable Worlds Observatory reads the paragraph, and what comes after that, what you do when you have read the paragraph and understood it, is a question that the next generation will have to answer. But there is a question that sits between those two instruments, between the sentence Webb is reading and the paragraph the next telescope will read, that has begun to occupy a particular corner of the scientific conversation in the wake of the Proxima b results. It is a question about what we would actually do if the answer came back positive, not in the abstract, philosophical sense that conversation is centuries old and has produced entire libraries of speculation. In the specific, logistical, civilizational sense, what does a species do when it confirms that it once had a neighbor 4.24 light-years away and that neighbor is gone? The answer, in the immediate term, is more science, more observation, more characterization. The scientific community's response to a biosignature confirmation would not be to launch a spacecraft toward Proxima Centauri, not immediately, not for a very long time, because even the fastest spacecraft humanity has ever built would take tens of thousands of years to cover that distance. The response would be to understand what the signal actually means, to determine whether the life it implies was microbial or more complex, to determine when it existed and when it ended, to determine whether anything remains, however diminished, in whatever niches the declining atmosphere of Proxima b might still support. That last question, whether anything remains, is one that the current data cannot answer and that the follow-up campaign can only partially address. The dimethyl sulfide signal, if confirmed, would tell us that something biological is, or recently was producing that molecule in the planet's atmosphere. It would not tell us where on the planet, it would not tell us what kind of organism, it would not tell us whether the production is ongoing or whether it represents the decay of biological material left behind by organisms that died before humanity existed. The atmosphere carries the chemical legacy of whatever happened on the surface. It does not carry a timestamp. Determining whether Proxima b hosts extant life, life that is alive right now, today, in whatever form it takes, versus relict biosignatures from extinct life, is a problem that may ultimately be unsolvable from Earth's distance with any instrument we are capable of building. The spectral signatures of living organisms and recently dead organisms are not dramatically different on the timescales involved. A planet where life went extinct 1 million years ago might look, from 4.24 light-years away, very similar to a planet where life is still clinging to existence in deep subsurface environments or hydrothermal systems shielded from the worst of the stellar radiation. The atmosphere integrates signals from the entire planetary surface and does not easily distinguish between a thriving biosphere and a dying one. This is one of the most sobering realizations that the Proxima b results produced for the astrobiology community. The dream scenario, a biosignature so clear and so strong that it announces itself unambiguously as the product of a living, active biosphere, may not be the scenario that Proxima b offers, even if life is or was present. The scenario Proxima b may offer instead is something more ambiguous, more difficult to interpret, more resistant to the clean headline. A world where life happened or is barely happening and where the evidence for it is faint enough and the alternative explanations numerous enough that certainty may be permanently out of reach from our current vantage point, not a discovery, a strong suggestion, compelling enough to change the way we think, insufficient to close the question. The scientific community has a term for this kind of result. They call it a candidate biosignature, as opposed to a confirmed biosignature, and the history of astrobiology is littered with candidate biosignatures that generated enormous excitement and then dissolved into ambiguity over time. The 1996 announcement of possible fossilized microbial structures in the Martian meteorite, ALH 84001, was perhaps the most famous. A finding that generated a White House press conference, a statement from the President of the United States, and a cascade of follow-up research that ultimately produced no consensus and left the original claim in a state of suspended judgment that persists to this day. The lesson the community drew from that episode was not that biosignature claims should be suppressed. It was that the threshold for confidence must be higher than enthusiasm, and that the process of building towards certainty, while slower and less satisfying than a dramatic announcement, is the only process that produces results the scientific edifice can stand on. Proxima B's dimethyl sulfide signal is being handled in the spirit of that lesson. The original paper flagged it carefully, hedged it appropriately, and called explicitly for follow-up rather than drawing conclusions. The follow-up campaign is designed to either build confidence or eliminate the signal. The community is proceeding as it should, but the existence of the signal, even as a candidate, has already changed something about the texture of the conversation around astrobiology and the search for life. It has made the conversation more grounded, more specific, more tethered to actual data rather than to the theoretical frameworks that had, in the years before Webb launched, begun to feel increasingly abstract given the absence of any observational anchor. The observational anchor that Proxima b provides, even in its current ambiguous state, is the most valuable thing the data has produced. Not the tentative biosignature, not the cold trap mechanism, though that is significant. The most valuable thing is the fact that there is now a real world, at a real distance, with a real data set, that the entire astrobiology community can orient itself around, a target that is not hypothetical, a measurement that is not a model, a question that is no longer purely philosophical. There are 47 known rocky exoplanets within 40 light-years of Earth that currently sit within the estimated habitable zones of their host stars. 47 worlds that the Habitable Worlds Observatory, if it performs as designed, will be able to characterize in some degree of detail over its operational lifetime. 47 potential data points in the distribution of planetary habitability around our stellar neighborhood. Before Webb looked at Proxima b, those 47 worlds were essentially theoretical, known to exist, but unstudied at the atmospheric level, their habitability potential assessed entirely through models and estimates. After Webb looked at Proxima b, those 47 worlds have a context. They have a framework. They have a comparable example, the first observational entry in a catalogue that is just beginning to be filled. The value of that first entry is difficult to overstate. Not because Proxima b is the most favourable of those 47 worlds in terms of habitability potential, it may well not be, but because it is the closest. Because the data quality achievable at 4.24 light-years with any given instrument is orders of magnitude better than the data quality achievable at 20 or 30 or 40 light-years. Because Proxima b will be the most thoroughly studied exoplanet in history for the foreseeable future, and the lessons learned from studying it will inform every observation made of every other world on that list. It is the calibration standard. It is the reference point. Whatever it turns out to be, post-habitable rock geologically active remnant world, or something carrying the chemical trace of biology, it will be understood in more detail than any other world beyond our solar system, and that understanding will be the foundation on which the rest of exoplanet science builds. This is a perspective that sometimes gets lost in the immediate drama of the biosignature question. The dimethyl sulfide signal is gripping. The possibility of a neighbor, past or present, is compelling in a way that engages something fundamental in the human imagination. But even if that signal dissolves in the follow-up campaign, even if the most pessimistic interpretation of the data turns out to be correct, and Proxima b is simply a cold, trapped, geologically active, atmospherically declining rock with no biological chemistry anywhere in its history, the scientific return from Webb's observations will have been transformative. The cold trap mechanism, observed directly for the first time, the secondary atmosphere dynamics of a tidally locked planet, characterized with real data, the rate of atmospheric loss under red dwarf irradiation, measured rather than modeled. These are fundamental advances in planetary science that will outlast the biosignature debate, regardless of how that debate resolves. And yet the biosignature debate is the one that will keep people awake at night. That is the nature of the question. Science proceeds through incremental advances in knowledge, through careful measurement and cautious interpretation, and the slow accumulation of consensus. But the question underneath the science, are we alone? Did life happen somewhere else? Did the universe produce something like us in another location? Is not an incremental question. It is an all-or-nothing question in emotional terms, even when the data is continuous and gradual. And Proxima b, sitting at the exact center of that question, draws the full weight of its emotional significance, regardless of whether the scientists studying it want it to. There is something worth sitting with in the specific character of what the Proxima b data describes, taken as a whole, not just the atmospheric chemistry and the thermal profiles and the spectral features, the whole picture. A world that formed around a star that is older than our Sun, in a system that has been running for longer than our own solar system has existed. A world that sat in the habitable zone of its star for billions of years, under conditions that were, by the current best evidence, not uniformly hostile to the emergence of life. A world whose geological activity, the churning of its interior, the cycling of its chemistry, the slow outgassing of its volcanic systems continued for long enough to maintain a secondary atmosphere detectable by our instruments today. A world that, in the language the data speaks, was doing something, chemically, geologically, perhaps biologically, and a world that is now, by every metric available, past whatever peak it reached, cooling, declining, moving over billions of years, still ahead of it, but moving in the direction of the barren simplicity of a world that has spent its energy and is now just coasting in the dark beside a star that will keep burning for 4 trillion more years after the last molecule of anything interesting has been swept away. The picture is not of catastrophe, it is of completion. The sense that whatever Proxima b was going to do, it has largely done it. And what remains is the long, quiet aftermath. The geology still running because geology is stubborn and slow to stop. The atmosphere still present because the interior is still warm enough to replenish what is lost. But the trajectory clear, the direction established, the story in its broad strokes already written. What that story contains, whether the chapter between the planet's formation and its present state included anything we would recognize as biology, is the question the follow-up campaign is designed to answer. but the shape of the story is already visible from the data. A long beginning, a middle that the current evidence suggests was more interesting than the end, and an end that is still playing out, slowly and quietly, in the thin remnant atmosphere of a world nobody will ever visit. Nobody will ever visit. That sentence carries a weight that is easy to pass over, but worth holding for a moment. Proxima b is the closest exoplanet we will ever study. It is 4.24 light-years away. The fastest spacecraft humanity has ever launched, Voyager 1, currently the most distant human-made object, travels at roughly 17 kilometers per second. At that speed, reaching Proxima Centauri would take approximately 73 years. The most optimistic proposals for interstellar spacecraft, the Breakthrough Starshot initiative, which imagines accelerating a gram-scale probe to 20% of the speed of light using a ground-based laser array, would reduce that travel time to about 20 years. But those probes, even if the technology ever becomes feasible, would arrive at Proxima Centauri carrying cameras and sensors, not humans. And a gram-scale probe travelling at a fifth of the speed of light does not slow down and enter orbit. It flies through the system in a matter of hours and transmits whatever data it gathers during that brief passage back to Earth. A flyby, not an expedition. There is no scenario on any realistic technology roadmap in which a human being stands on the surface of Proxima b and looks up at the red, dim light of Proxima Centauri and tries to read the geological record of what happened here. There is no scenario in which a geologist picks up a rock from Proxima b's surface and carries it back to a laboratory. There is no scenario in which a rover slowly traverses the terrain of Proxima b the way rovers have traversed Mars, or the way future rovers may traverse Europa or Titan. Proxima b will be studied for the foreseeable future of our civilization entirely through light, through the photons that travel from that world to our instruments at the speed of light and carry, encoded in their wavelengths, whatever information the planet is willing to give up. We will know that world only through its glow. We will understand it only through what it chooses to radiate into the darkness. This is not a limitation unique to Proxima b. It is the fundamental constraint of observational astronomy. But that we will receive the news of our nearest neighbour's biological history in photons. That the closest we will ever get to knowing what happened there is a spectrum, measured by a telescope, interpreted by a model, argued about by scientists, and eventually, if the data is good enough and the follow-up thorough enough, agreed upon as the best available truth about a world we will never touch. There is a melancholy in that, and there is also something that feels appropriate about it. The universe communicates in light, it always has. Every star in the sky, every galaxy in the deep field images, every nebula and pulsar and quasar and black hole we have ever studied has been studied through its light. Light is how the universe tells its story to any observer far enough away that physical contact is impossible. Which is to say, light is how the universe tells most of its story to most observers most of the time. Proxima b is no different in this respect from any other object we have ever pointed a telescope at. It is just closer. And closer means the story is told in more detail, more wavelengths, more signal, more data, a richer account, if a still remote one. The richness of the account Webb has provided, and that future instruments will continue to build on, is already more than anyone standing at the moment of Proxima b's discovery in 2016 had any realistic expectation of receiving. In 2016, the planet was a statistical inference from the wobble of a star, a mass estimate and an orbital period and a position. 8 years later, it is a world with a measured atmospheric composition, a characterized thermal profile, a documented geological signature, and a tentative biosignature candidate that the scientific community is actively pursuing. The rate of knowledge accumulation driven by the capabilities of Webb has been extraordinary, and it will continue. The next observational milestone within the Webb campaign is expected within the next 2 years. The cumulative signal strength from the follow-up observations will reach, by current projections, the level required to make a statistically meaningful statement about the dimethyl sulfide feature. Not a definitive statement, a meaningful one. A statement that will either shift the probability substantially toward the signal being real or substantially toward it being noise. That statement, when it comes, will be the most anticipated result in the history of exoplanet science. Not because it will end the debate, because it will tell the community which direction to push harder. If the signal strengthens, the resources allocated to understanding Proxima b will multiply. Additional Webb time. Accelerated planning for the Habitable Worlds Observatory mission. Proposals for the Breakthrough Starshot initiative gaining new urgency and new funding. A global scientific conversation about what a confirmed past biosignature at 4.24 light-years means for the search for life elsewhere, and for the philosophical and cultural self-understanding of the human species. A conversation that will be impossible to contain within the scientific community, and that will spread, as such conversations always do, into every domain of human thought and expression. If the signal weakens, something different happens, something equally important, though less dramatic. The most optimistic interpretation of the Proxima b data is set aside. The cold trap mechanism and the post-habitable classification stand. The timing problem for red dwarf habitable zone planets is reinforced. The catalogue of rocky exoplanet atmospheres, of which Proxima b will be the first entry, begins with a world that was geologically interesting and atmospherically declining, but showed no confirmed biological chemistry. That is not nothing. That is the first empirical data point in the distribution of rocky exoplanet atmospheric chemistry, and its value to the long-term scientific program of understanding how common life is in the universe is enormous, regardless of whether it contains a biosignature. Either outcome advances the science, either outcome moves the human understanding of our place in the universe forward in ways that were not possible before Webb looked. The difference between the two outcomes is not the difference between progress and stagnation. It is the difference between two different kinds of progress, one of which is more emotionally charged than the other. The emotionally charged kind is the one the human imagination tends toward naturally. The possibility of a neighbor. The possibility of not being alone, even in the past tense. The possibility that 4.24 light-years away, on a world we can study with light but never visit, something once lived and breathed and metabolized and produced gases that drifted into an atmosphere that thinned over billions of years and eventually became faint enough to be measured by a telescope built by the species that came after, on the next rock over, just late enough to almost miss the signal. That narrative, the one about timing and proximity and the specific, quiet tragedy of arriving just after the story ended, is the one the data seems to be telling. Not definitively, not with the confidence that science requires before it will say something is true, but in outline, in the shape of the evidence as it currently stands, before the follow-up campaign resolves the ambiguity one way or the other. It is a narrative that does not require a confirmed biosignature to be meaningful. The post-habitable classification alone, the identification of Proxima b as a world that was once more favourable and is now less favourable, that crossed a threshold from one side to the other at some point in the billions of years of its history, carries an implication for our understanding of the universe that stands independent of whether life was ever involved. It says that the universe produces worlds in decline, that the habitable zone is not a permanent condition, but a phase, that planets pass through windows of potential and then pass out of them, that the cosmos is not static in its hospitality but dynamic, and the dynamism has a direction, and the direction is not always toward greater complexity and greater potential. That is a lesson that sits quietly underneath the more dramatic question of biosignatures, and it is a lesson that the Proxima b data teaches regardless of how the dimethyl sulfide debate resolves. The universe is not waiting for us to be ready. It is not holding conditions stable while we develop the tools to detect them. It is running its processes on its own timescales, and those timescales are indifferent to whether any observer is present to record them. Proxima b has been declining for billions of years and will continue declining for billions more whether or not humanity ever measures the rate. The cold trap has been operating since before the first complex organisms appeared on Earth. The atmosphere has been thinning since long before the first telescope was built. The countdown has been running since before there was anyone to count. We built the telescope. We pointed it at the right place. We happen to be here now at this specific moment in the history of our civilization and the history of that planet, when the signals are still above the detection threshold, when the atmosphere is still thin enough to show spectral features, but not yet so thin that it has nothing to say. We caught it in time, just barely. And what we caught in those hundreds of hours of infrared data from a telescope 1,000,000 miles from Earth looking at a star 25 trillion miles away is either the chemical ghost of a world that once produced life or the natural chemistry of a world that never did. The difference between those two interpretations is everything, and we are right now in the process of finding out which one is true. That process will take years. It will be careful and methodical and full of the ordinary frustrations of science, instrument noise and model uncertainties and competing interpretations, and the slow grind of peer review. It will not be televised in real time. It will not produce a single dramatic moment when the answer arrives. It will produce a gradual accumulation of evidence that eventually tips in one direction or the other past the threshold of scientific consensus. And when it does, the world will learn what kind of universe we live in. Whether the nearest other potentially habitable world to our own was once, in some form, alive. Whether the chemistry of biology is something the universe tried in our neighborhood, within reach of our telescopes, close enough that the light from that attempt reaches us in just over 4 years. Whether we are alone in the way that has always been feared, or alone in the more complicated way, the way that comes from timing, from arriving after, from being the second attempt in a neighborhood where the first attempt ran out of clock. Both possibilities are profound. Both are worth sitting with in the dark, in the quiet, with the kind of attention that the question has always deserved. The universe is 13.8 billion years old. Proxima b has been orbiting its star for roughly 4 billion of those years. Humanity has been capable of building telescopes for a few hundred. The James Webb Space Telescope has been operational for a handful of years. The window during which it is possible for us to detect the atmospheric remnants of whatever Proxima b once was, before the last of the signal fades below the detection threshold of any instrument we will ever build, is not infinite. The timing, as always, is the whole question. We looked at the right time, we built the right instrument, we pointed it at the right place. What it found is sitting in the data, patient and quiet, and 4.24 light years away, waiting for us to be certain enough to say what it means. We are not there yet, but we are closer than we have ever been to knowing whether, in the only other place we have ever been able to look this carefully, the universe tried to know itself twice, and whether the second try ran out of time before it could. The stars do not hurry, they burn at the rate the physics demands and no faster. Proxima Centauri will burn for 4 trillion more years, long after every sun-like star in the galaxy has exhausted its fuel and faded, long after the Milky Way has merged with Andromeda and the merged galaxy has settled into whatever new shape the collision produces, long after the cosmic microwave background has redshifted so far into the infrared that no instrument will ever measure it again. Proxima Centauri will still be there, dim and red and patient. And Proxima b will still be orbiting it, a bare rock by then, most likely, or close to it. The last traces of its secondary atmosphere long since stripped or frozen. The geological activity of its interior finally quieted after billions of additional years of cooling. A world that has become, by then, simply a rock in a stable orbit around a stable star. Unremarkable except for what it once was, or might have been, in a window of time so far in the past that even the light from that era has long since travelled beyond the observable universe. We will not be there to see that ending. No human civilization operating on any timescale that biology or culture can sustain will persist long enough to witness the final state of Proxima b. We are observers of a single moment in that planet's history, a moment we happened to reach at exactly the time when the instruments capable of reading that moment's story had just become available. The convergence of our technological development and the planet's current state, still atmospheric enough to study, still geologically active enough to produce readable signals, still carrying whatever chemical legacy its history has left in its thin air, is not a coincidence in any cosmic sense. It is simply where the two timelines happen to intersect. Our civilization's timeline and Proxima b's timeline running independently for billions of years, crossing at a single point that we happen to occupy. That crossing point is now. This is the moment. The data is here. The follow-up campaign is running. The next generation of instruments is being designed. The question is live. And somewhere in the photons that Webb collected, in the wavelengths that travelled for 4.24 years from a dim red star and its declining rocky companion to a gold-plated mirror in space and down into a detector and through a data pipeline and onto the screens of scientists who went very quiet when they saw what was there. Somewhere in all of that is an answer. We are, right now, in the process of reading it.